So welcome back to day number 2. Today we're going to pick up with shell scripts and talk about shell programming. This one is lecture number 6B. So we have number 6B on Introduction to Shell Script Programming. I already covered 6A several weekends ago, or that was the last weekend we covered 6A. Had some shell commands. So today's about scripting and what the different environments you're doing. So understanding the program development lifecycle for scripting. It's just kind of a software engineering topic, so I'll just show you what the model looks like, essentially, for most script development projects. I compare Unix, Linux shells, and creating scripts, and using shell variables is what the big part is, and operators and wildcard characters, stuff like that. So using shell logic, and employing shell scripting to create a menu. That's kind of an old-fashioned way of doing it, but menus are still helpful now, especially when you're looking with the command line. Customizing things and using a trap command, actually. So we'll see a shell script that uses a trap command as well. So in terms of previewing the application, shell scripts can be used to customize your environment. So it's not like an application, like a program somebody's running. Instead, you write a script that's going to automate your work. So going back to what I said yesterday, computer's working for you. You have to tell the computer what to do. So you write a script so that the computer can accomplish everything while you're offline. So if you're doing that, then you're going to customize your environment variables. You're going to write some routines to do some tasks at certain times. You may not necessarily use time. It might just be a sequence that runs. You might put it on a scheduler program. There's a lot of Unix scheduling that goes on for jobs and things, clean up stuff, do some routine tasks. So we'll develop a simulated employee information system using shell scripts. I'll show you how that's done. And then using regular database, or not database, using regular files instead of a database. But you can easily modify it to use an SQL database as well. Most Unix environments have databases built into it automatically. So it's like MySQL or something, or Oracle sometimes, because Unix and databases get along well. It's a great way of storing data outside of the file system. So you might write a shell script that does database maintenance for you or something. Getting experience with shell variables, shell operators, and logic structures. So the program development lifecycle, you sort of have to treat it like software engineering. It's kind of an interesting concept. Looking at the process, first step is going to create the program specifications. If you don't know what the script is supposed to do, the script might be doing something that's not what you'd think it would be doing, and then you run the script and you have something else happening. The problem with scripts is that maybe you only want certain accounts to be backed up, or maybe you only want certain things to be done. You put it all in one script, you don't have a choice. You got to cut and paste out of the script and put it and run the stuff manually. So instead of writing just one script that does all your work, you write smaller little ones that are well defined in terms of the requirements, label them properly, and then usually you end up with dozens of these scripts. So it's not a one script fits all kind of environment. A lot of people try to do that with programming, however. They try to write one program that does everything. It's like, no, it's like the exact opposite thinking. So get out of programming mentality and get into like single task operations, and then you're a good scripter. The second step is to create the program design. You might be thinking, well, I'm not making a program. You are, actually. So you almost have to think of it like a program design. In fact, you could do UML. You could do a software development lifecycle model, the requirement spec analysis, design. You could do the whole 9 yards for a script. So don't devalue the purpose or the concept. It's the same as writing a full-fledged development program. And third step is developing the code, which is written, tested, and debugged. Yes, it is written, tested, and debugged, just like regular programs are. So here's your program development lifecycle if you don't actually know what I'm talking about. In the beginning here, we have the beginning of the process at the top. Program specifications, program design, writing the code, testing the code, going through a bunch of series of iterative steps to get the script perfected. And then finally, the script just sits on your Unix server. When people log in, as an example, the script runs. When people log out, the script runs, or something. That way you can monitor what your users are doing. Check out to see the port activity, who's transferring what, who's changing passwords, who's doing stuff on the system. A lot of scripts are used for analytics, gather data. about what's going on. And those could be automated. User logs in, script starts. User logs out, script goes away. Each one of you has about 4 scripts that run every time you log in. Tracks what time you logged in, how long you were there, sets your environment variables for you. Actually records everything you're doing, what directories you've changed to, everything. So, which people think might be borderline spyware, but it is. So, actually, you can write a lot of scripts that work on Windows computers to do spyware. It's pretty easy. Browser plugins and things. Scripts. They're just scripts. So write a macro, put it inside of a Word file, and really wreak havoc on your victim's computer. But long story short, we're not writing viruses here. We're writing Unix scripts. And normally, we're going to use a higher level language for that. And you're wondering, well, what do you mean? You can write Unix scripts in C. You can write them in C++. You know, there's no difference between a C program and a script program. In fact, the C shell, you write native C code, and it's a script. So don't think that scripts are not programming. They are. So high-level languages and computer programs that use English-like expressions, examples of those would be COBOL, C, C++. Or you could use high-level statements that are stored in a source file, which programmers create using an editor, normally, which is the concept of programming languages. So they have to be converted to a low-level machine language if you're not going to run it on a Linux box. Actually, on Linux, you have less of the machine code requirement because you have things like languages like Perl and Python and PHP where there's not any pre-compilation. It's only in your non-Windows systems do you have most of the requirement for an executable binary file versus a script. So the compiler converts the source code into machine language and runs the files for you. If the source code contains syntax errors, it converts it and checks it for you into the executable file. It won't create the executable file unless the errors are checked. So the style of programming is write it, check it, and it's about the compilation process. It doesn't compile, then you fix the errors. Script, you can't do that. There's no compilation. So you run it and you see what happens. And in the meantime, what happens is it copies directories or does something, and you go, oh, and then you fix the errors, usually on the Unix system because it's running and it's doing stuff, so which is the purpose of the script. So it's a little bit trickier. So people spend a lot more time troubleshooting scripts than they do programs because you can't afford to have too many errors with that. And you have no compilation process, so you've got no way of testing it from the executable level. Problem with the executable file is you make it, you think it works, and you give it to a user and it destroys something on their computer. Or it does something, and you're like, oh, well, it worked on my computer. Yeah, see, the flip side of that is on the Unix, works on one system, works on all systems. It doesn't have any side effects like that, for the most part. I'm not saying there can't be, but you might not have a directory that exists, that's supposed to exist or something. And if that's the case, the script normally doesn't just bomb out on you completely. It'll try to recover. It goes to the next line, to the next line. So just keep in mind, you don't have to correct anything before moving on to the next program and before making the program work. So unlike high-level programming languages, shell scripts do not require to be converted to a machine language. So the interpreters, the loader and the linker and the interpreter are running real time. They're running when the program is actually being executed. And interpreters read the statements in the script files themselves, interpret, translate, and put them into executable instructions, and then run them. So all of this stuff happens at a delayed instead of an early binding of everything. You have a late binding of everything, and everything's delayed. So the interpreter runs the script and figures out what's going on with that. So using scripts themselves, after creating the script in a text file, you give the operating system instructions. We did this in assignment number 1, 755 says it's executable. That's equivalent to creating the binary code, or the machine code, I should say, in the exe file, or exe file. So script files run in a couple of different ways. You set the path and the type of the script name at the command prompt. You type in the // file name to run it, and then or you just type in the script name, the full path. So prototyping an application. So you can write a full application in this fashion, with variables and iteration and flow control and recursion and everything. Just everything you've done in programming you can do in a script. So when the prototype of a running program is created, there's a little bit less detail, less design than a full application. But what you're doing is kind of going through the steps and printing stuff out to the screen that says, okay, database was backed up. Okay, user accounts were checked for consistency. Report of log of usage was backed up or something. You can put like little printouts or something in the program statements. Shows potential without full programming effort. Usually, scripts can be used for prototyping applications and then move to compiled languages. A lot of people move back and forth. They make a script, prototype a big application, and then take the script and put it into C and compile it. In fact, you can write the script in C, then compile it later to distribute it. So a lot of development is actually done from scripting for compiled languages as well. Not as much as anymore, but in the old days, a lot of that stuff was done this way. So using comments. So comments are important in the code, just like they are in C or C++ or Java. And it all starts out with that hash symbol. So, or the pound symbol, I should say. So you provide useful documentation to the programmers, and so they can understand what you're using. To use it, you start with a line and a pound sign. So the programming shell. We have programming shells, and then we have shells. The programming shells, for example, CSH or TCSH, conforms to scripting and programming languages. Formats the shell as an extension use of operators similar to those in the C programming language. It's not C like GCC, but it uses C. Let's see. We got corn shell, KSH, similar to bash shell, but also contains some C programming stuff. Also has scripting, different scripting commands. Bash, offering scripting and programming language features, variables, stuff like that. So what does that mean? Well, depending upon which shell you're in, you can actually use things like printf, scanf, regular old C libraries. As an example here, if I go into C shell, actually let's see, CSH, there we go. I can type something in like printf and go, well, isn't printf? Actually, I'm going to leave out the bracket because this version doesn't take the brackets. Hello world. Oh, let's put a couple line returns in here. Put a semicolon at the end, and look at that, I go, hello world. So a lot of people could test out, let's say for example, C expressions or C iterations to see, is this going to work without having to compile it and test the program? So a lot of C developers write C code in shells so that they can test out algorithms, routines, data structures, and things, and then move it over into a compiled version using GCC. Or you can actually just use GCC here after you've got it all made. Put it into a file, save it, and type GCC after you've run it. So it's a better development environment in terms of troubleshooting. It takes a little bit more work because you have to have access to Unix, or shell actually, in order to type those commands. It's not like running in an IDE of your general program. So anyway, so that's that one. Actually, I demonstrated the C shell. That one was, I typed in CSH to get to it, which is another reason why people switch shells. I can't do that in the Bourne shell or in the bash shell or whatever shell I'm in. It's not going to work unless it accepts C code, which it's not going to accept. Anyway, all Linux versions use the bash shell as the default, and bash supports environment variables and a bunch of other kind of interesting things that we're going to go over in a few minutes here. And I'm going to kind of sort of compare the shells with you for a while here, and kind of go back and forth and kind of see how the stuff works. So variables are symbol names. So usually when you write, I just wrote hello world, by the way. See how easy that was? Now if this were a C programming course, it'd take me like another hour to get you to compile, run, and I have to go around and fix syntax errors on half of your computers because it's not going to compile correctly because you left out, you capitalized main instead of lowercase main or something like that. So I'm going to actually write a program. This is pretty easy. So, or I'm going to try to write something. Let's see what happens here. Variables are symbolic values that store in memory. Remember, first if writing hello world, next thing we do is go integer I, integer x, float f, you know, and you just kind of, and then you go, okay, print out I and f and all this other stuff. And we can do all the same stuff. So syntax is a little bit different, but you're in a shell. You're not in a statically compiled executable file. Why not use the environment that you got? So a lot of scripters for C scripting, and actually it does not even talk about C, this should talk about scripting in general, will create set environment variables and use the environment for your advantage. Because you can just directly load it up into memory. There's no reason why to statically allocate I as an integer and assign a value to it and swap it back and forth. You can just have one global variable called I and stick it up in the environment and then use I in any script you want. What is I? It could be I could be the age of the user, or it could be a flag, on and off flag for some feature that they have or don't have. And then you can test for the value of I in 25,000 different scripts. Instead of going integer I, integer I, integer I, I'm not going to do this 25,000 times, but you'd have to do it 25,000 times to statically set that variable in every single one of your programs. Waste of time. So scripting is actually more efficient than programming for the most part. You set it once, you use it. You don't have to keep resetting stuff, which is kind of a troublesome part of programming. Every new program you write, if you're going to compile it into an executable form, you have to redefine your data. You can't take advantage of anything you used before. It's a different way of thinking. 3 types of variables in scripting: configuration variables, environment variables, and shell variables. So you can put it in the environment, you can put it in the shell, or you can make it part of the system itself, part of the configuration. So store information about the setup of the operating system. That's your configuration. That's your login script variables. It's going to be who you are as a user, how long you've been on the system, all these things that are set. Who sets those things? The admin sets them, puts it on your account. Environment variables hold information about the login session, only per session. And then we have the shell variables created on the command prompt or in the shell scripts and are used to temporarily store data. So environment and configuration variables, most popular type. You get that if you type in print env. So if I've typed in print env, I'm going to see everything I've got in my system here. And I got a lot of stuff in this system here. I got a terminal program is the Apple terminal. I'm not connected to the server. I'm on my MacBook. Oh, I got the terminal session ID. That's a pretty long ID. Program version. Got SSH. Oh, I got a listeners going on here. Oh, look at it. Here's my PWD. So when I type in PWD, I get that piece of information. It comes back. I can echo, as an example, home or echo. Let's just echo PWD. And then I get the same information. So echo, we learned in a couple of different assignments already, just prints out the environment variable. So we're going to take this a little step further and set some environment variables and use it in a shell script. So I just did this for you live. This is using print env to see the list of environment variables. That's kind of important because then you can know what you're working with. So one of the common ones, standard for bash shell, is home. Log name, PPID refers to the parent ID of the shell. So I can tell where I came into the system. TZ, time zone, IFS, default delimiter for working with files. It's redefinable as well. Here's some more. I'm not going to go through all of them, but these are some more common ones as well. Mail check, path, env, which is actually your environment. So groups, what groups do you belong to? Actually, I don't know if I belong to any groups. So more stuff here. So I'm not going to go through all of them. I'm just going to kind of thumb through here. PWD, you saw that one. Random, term, user ID. So these are called environment variables. You can use them in your scripts, no problem. So you already have access to all that information. So you don't have to ask the user who they are anymore. You can just tell what user it is. So you can write one script that picks up the user, what time they were logged on, and what they did by following their command buffer and following and pulling stuff out of the environment. Everything you do is stored in the environment. So pulling the session information out, looking at it, which is what the Unix kernel does actually, and just record all of the user's activity. Great way of testing to see who's doing what on that server. Yeah, history. Yeah, well, just pull it out of the history. Yeah. I mean, it's all recorded for you anyway per session, and then the admin has copies of all the histories and can just archive the histories.
I can show all the comments that users used.
Yep. So technically, I can figure out who's been messing around with those passwords for those unlucky students. Actually, I did the other day, and I did find out. So, and it was one guy, as I suspected. But I haven't contacted him yet, but we'll see what happens with that. It could have just been stupidity, you know? He probably just didn't know his student number because he was off by 1 on one of the ones he kept taking down about 4 times. People are just stupid. You know, they'll just log in and then, oh, it doesn't work. Log in again, log in again, log in. It's like brute force or something. Do you think if you provide the wrong password 20 times, actually it only goes to 3 times, do you think that's going to help anything? But people are just, you know, it's like the guy who's the door's locked, so he's going to check the door, check the door. The door's still locked. The door's still locked. I mean, what are you going to do, bang the door down? It's kind of like our gate. Did you guys notice the gate? You probably didn't notice the gate. I went through it and it was like, I'm like waiting for the bar to go up. There's no bar. So somebody probably tried to get in or out or something. Probably get in because it's the in gate. And just ran through the wood stick that goes across. But it's kind of pathetic. It's a wood stick. Well, my car probably couldn't do it, but any car could probably break the gate thing. So, anyway, long story short, lots of stuff's in the environment, and lots of stuff can be kept and stored and manipulated. So variables are important. So this stuff I'm talking about are variables. So variables can be defined, manipulated, and used with program commands in the shell. Observe the basic outline for handling the naming shell variables. Here we go. So let's talk about bash, and I'll have to go back to bash when I use these things. Shell operators are in 4 groups. We've got defining, evaluating, arithmetic, and redirection operators. So it's used to assign a value to a variable, most commonly as the equals. So x is equal to 1 or something. So use quotation marks with strings, just like you do. Actually, you saw me with printf. Back quotes say that execute the command inside of the quotes and store the value in the variable. So used to determine, in terms of the evaluation operator, it's used for determining the contents of the variable. So if I have home as the name of the variable, I use the $ home, and I can put it in front of echo if I wanted to. And then it would evaluate the expression and give me the answer, or whatever's stored in home or variable name. And then double quotes are used, but not single quotes. So single quotes are never used, only double quotes. So here's an example of some of the things we've used for unary, minus, and plus. Plus R, minus R. We've seen this with change mod. It's the same stuff you get in the Unix commands that you use in the scripting. The not, the exclamation point, multiplication, the greater than or the less than for redirection, the exclamation point equals for not equals, stuff like that. So here we have one. It says let, and let is the key. So we don't have data types, by the way. Well, we do have data types, but we don't have to use them. We can have a typeless system going on here. So regular mathematical expression. So we have rules apply to arithmetic operators. So to store the arithmetic values in a variable, you use let. So this example here is saying let x is equal to something and then echo x. So if I were to look at this, I could say, let me clear my screen out so it looks better. Let me exit out of this shell, I'm back in the bash shell. So let x equal 1, 2, 3. And then let y equal hello there. Oops, single quotes. Oh, wait a minute. Syntax error expression token is there. Yes. Let's just do it this way. There. Then I can go echo x, and then let's give it y. Then I got 1, 2, 3, 0. And you're going, well, what happened with that? Wait a minute now. And why did I have to do that? You have to follow some special syntax. So it's not that way, but let's just take a look here and we'll see what's going on. But for numbers and for expressions, numerical values, there's no quotes needed. You just add it in there. So the 1, 2, 3 actually worked. It was the hello there we had a little problem with. Let's take a look further on the syntax and we'll see what's going on with this. So using let and sets the contents of the shell variable. So then we have the redirection operator. Actually, let me go back for a second here. Probably if I use single quotes. No, I can't use single quotes. Well, we'll figure it out. Anyway, so the redirection operator is that arrow going forward. We used it with the cat already. Well, we can do it with variables. We can assign one variable to another variable, one output from one expression to another expression, and use that for our programming. So the forward arrow is the redirection operator, operates an existing file. So example, -o, no clobber. Option of set command will prevent overwriting. So -o, so no clobber means don't overwrite, don't clobber it. Don't overwrite the variable, leave it alone. If it already exists, don't overwrite it. So exporting shell variables to the environment. So shell scripts cannot automatically access variables. So if you've created and assigned them on the command line or by other scripts, so you have to use exports. So make variables global in your environment by using export command next to them. Export means it's not only in your script, it's elsewhere in the environment. Path variables control where your shell will look for the shell scripts. So you can set the path in there. So you can add directories to your path, special directories for scripts, special working directories. And then we have these wildcards we saw yesterday. Wildcards can also be used in scripts. So I'll have to use wildcards here. Wildcards are called glob characters by default. And they are part of the glob patterns. So you don't really see the word glob used very much, but it's like a glob, gobbledygook. You have a glob of stuff. It means stuff or matter stuff, glob. So they're glob characters, which means we don't know what it is. So we're going to use a wildcard to figure out what it is. So the question mark matches one character, the asterisk matches one or more characters, and then characters defines the characters of the glob pattern. So shell logic structures, if, then, else, sequence, decisions, do, whiles, all that other stuff, 4 basic logical structures needed for the program. Sequential logic, decision logic, looping logic, and case logic. So for our sequential logic, we have commands that are executed in the order in which they appear in the script or the program. One line after another line after another one. This is procedural programming, by the way. It's not object-oriented programming. It's like C. This is more like C. Where we're just going from the top of the code or the top of the script to the bottom of the script. So only break in the sequence comes when a branch of instructions changes the flow of the execution or redirecting to another location or script or part of the script or program. So you can use go-tos actually in your scripts if you wanted to. So you go down, 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 go to, skip a bunch of statements if you wanted to, and then go back if you needed to. Used for simple, straightforward command sequences. And then we have decision logic. Enables your script to program or to execute statements or a series of statements only if certain conditions exist. If x is equal to 1, 2, 3, or if this condition is true, if the user is logged in, then send a message to the user that says, hello, how are you, or something. So in many cases, that condition depends upon the results of the commands or comparisons that are made, and the if statement's used for that. So we have if. Actually, we have if, else, then. We have all that stuff, part of the structure. And for and while loops. Most of the stuff that's in C, which makes C a good programming language for Unix people to learn, because all the stuff that's in C is in the shell scripting environment in terms of the iteration flow control. So the control structure repeats until something happens, something exists that breaks the looping. 2 common looping mechanisms, the for loops and the while loop. For is for counting cycles. So for x is equal to 5, x is less than 10, x plus plus, how many times you're going to go through the loop. It's usually for count, you know the number of times you're going to go through the loop. Or while loops when you don't really know exactly how many times, you're just going to set it so while some condition exists, then do something. So here's an example of the for. So the for loop repeating for however many times or values that are in the specified set of the values. So here, do, echo, my hobbies, done. And this is the actual hold on a second. 4 hobbies in tennis, swimming, movies, travel. So my hobbies is a text file, and in my hobbies there is a tennis, swimming, movies. Actually, in there's tennis, swimming, movies, and travel. So if you were to make this file, you could make a file called My Hobbies, put in a bunch of hobbies on each line, and then for my hobbies in tennis, swimming, movies, travel, then echo it to the screen. What are you going to echo to the screen? My hobbies. Done. So we got tennis, swimming, movies, travel. And then we're back. So it's a way of writing a for loop without actually having to know how many things, but you're using the content of the file to control how many iterations goes through. So we have all of the items in the file being printed out while they existed. So the program I'm not going to bother typing them in. So the program control structure can be entered from the command line, as we've seen. Wildcard characters can be used in loops, and the while loop is set up to test repeatedly for a matching condition. So we have this undetermined number of time. The while loop goes for an undetermined number of time, where the for loop goes for some sort of a certain predetermined number of times. And then the case logic. So the case logic was when the selection is from a list of choices, case A, B, or C, or 1, 2, or 3, or something. So it allows the script to perform one or many actions depending upon the value of the variables. So the 2 semicolons terminates the action after the cases have been tested. So you put 2 semicolons at the end. So you might be wondering, well, this is not exactly C. Nope. In fact, this for loop looked a little different than a for loop in C. So it's actually a little bit better. It's the scripting version of C. So it's a lot actually more flexibility, more intuition. C from a GCC implementation is a lot more rigid, a lot more structured than this. So you can use a shell script to create a menu. Here's how we're going to do it. We're just going to print a bunch of stuff to the screen. So often useful for branches off of scripts. So you create 5, 6 scripts, put it on a menu, and then just select from the menu which one you want to run. The tput command is useful for creating those menus. And so you can initialize the terminal display and put text on the prompt in a specified location and respond to the user. So we'll see an example here actually in a few minutes that uses tput. And then you can debug and check the script before you run it. So the shell environment, the shell script will not execute if there is an error in one or more of the commands. You can actually set the shell with these options before you run it. So if there's what you're doing is actually taking a shell, turning it into a compiled, like an executable, because it's going to pre-process all of the code in there and then tell you if there's an error before it runs, which is what you're doing when you create an executable. So you can run a shell using the sh, and enables a quick debugging of the problems, and that's going to be using a -v. So sh -v at the top of your script displays the lines of the script that are read by the interpreter. -x allows the display the commands and its arguments line by line as they're run. It's kind of like putting breakpoints and kind of doing a little bit of debugging with your shell script if you wanted to. So customizing your personal environment. So when you're running it, you're customizing and modifying initial settings and login scripts and providing many benefits. So what a lot of Unix programmers do is they customize their own login scripts and their own daily scripts that they're using for certain things to automate what they're doing. So automatically take them to a directory instead of leaving them in their home directory, or automatically run a script or do something so they don't have to do it manually. So login scripts just run after you log in. So you can actually add scripts to this too. So I log in, and then I have these 20 scripts that run sequentially. And then I can get all my work done while I'm watching TV or at the beach or something. So setting up your personal bin directories and modifying the editor defaults are common customizations. So customizing your personal environment, an alias is a name that represents another command. You don't like the way the commands are written in your shell environment, you create a bunch of aliases. So now I can use printf, or I can use print, or I can use p if I want to instead of printf. So you create aliases. The bash RC is used to make customizations to your login. We saw this actually in the first weekend. We looked at the bash RC file that was in the user's directory. It's usually a hidden file. It's hidden because of that dot that's in front of it. It tells it's a hidden file. The bash RC file is executable each time a shell is generated, such as when the shell scripts are run. So if you put a shell at the top of the file, then this is going to actually run automatically as well. Every time your script, every time a shell is opened up, this is going to run. So the trap command is an interesting command. So it causes a shell to automatically remove temporary files created when your shell script runs. So you can automate the temporary file creation using trap. And programmers often set up a subdirectory, let's say, to store all of the different files that are going to be used, temp files, and then trap removes the files. So if you set up a directory during the process of the script, you can run a trap to get rid of the directory. What does that do? GCC does the same thing. GCC, when you run it, it's a script. It creates your executable files for you if you have a C program. And so you have a lot of temporary .o files and a lot of ACM files, or ASM, I'm sorry, files, and a bunch of temporary stuff. Well, then trap is run at the end, and it cleans up all of those files for you automatically. And then you're wondering, well, why do I have to worry about trap? I'll never run it. Thing is, if you don't kind of look into some of the automated ways of working in the environment, then you're doing a lot of work manually that you don't have to do, actually. So Unix people, they like to look at the automated way of doing something, because the idea is not to spend your entire life on the computer. Do it most efficiently as possible. So programmers can set up subdirectories and things, have them removed. So having these files removed from the temporary directory like this creates good housekeeping, yes. Gets rid of the clutter, gets rid of the temporary files and stuff. I wish Windows would do some of that, because when you save a Word file example, or you're working on a Word file, there's like 20 different temp versions of that file that never go away. You take a look at your hidden files, you see all this garbage. Then you should just run a trap and just get rid of all that stuff. So putting it all together in an application, what you're doing is developing smaller pieces to put it together. So the applications require you to assign and manage variables, use shell operators, and employ shell logic structures, additional wildcards, use a tput to make the screen initialize correctly, and then trap to clean up your files and stuff. So in a high-level language, using an English-like expression, you have to convert all of this stuff to a low-level language to write the source code. The point trying to be made here is that you don't have to do any of that. You just take the logic that you would put into the program and write it with shell environment variables and shell instructions instead. So Unix shells have been derived from Unix Corn, and C shells, Bash as being the default. And that the three types of variables are the configuration, environment, and shell. And defining, evaluating, and redirection is important to know. Wildcards itself are good as well. So. And the tput command manages cursor placement on the screen. We're going to see an example of it coming up in a few minutes. And the programmers, generally administrators, change the .bash RC file when they want to customize their environment. And that's used for different commands that they want to run, and aliases that they want to create for environment variables or for shell commands. And you can use trap to clean up files. So 6C actually has the implementation and the examples of these things. So we're going to go ahead and switch to 6C. If I can find 6C. And somebody's phone is ringing or something. Here we go. Here's 6C. Let's just make sure this is the right one. It is. Okay. So 6C is the implementation of those things that were mentioned towards the end of the last lecture. So I'm going to skip to the beginning because I just gave you the last lecture. If this had been like a multiple repeated class, I'd have to refresh your memory on what we just looked at. So here it is. I'm refreshing your memory. Okay, refreshing it over. If you want, you can use Nano or VI. Normally all the scripts are created in a text editor. That's what this slide is telling you. So that you can format record output, delete records using a script, we're going to work with files for this script. So we're going to set up a quick screen clearing technique using a clear command and create a script or an algorithm to solve a cursor positioning problem. And develop a test program to eliminate duplicate records, and then create a shell function and use them in the programs. So ensuring the correct shell runs the script. That's the interesting part at the beginning. So you're going to put an indication at the top of the script as the first line of the script in terms of which shell you're going to have run. So each user, Linux user, can choose which shell they want by default. Ensure the correct shell is going to be used to run a script. Not all shells support the same command, so you'll want to make sure you're going to pick the one you're going to want. So setting the default shell, the system administrator establishes the default shell for the user, and that's going to be in the bash setup. So etc. PASSWD file. So you can find file can only be edited carefully by system administrator. You can't edit this file on your account, actually, unless you're doing it on your local computer. If you have a MacBook, you can edit your file, no problem. But if you make a mistake, it's going to be hard to get your terminal working again. So some systems provide management software to assist the users in terms of default shells. So using the bash profile and the login scripts. So when bash is the default, it runs automatically upon login or re-entering. So we have the .bash_profile and .bash rc also running at the subshell script level. Administrators control through etc. So it's located in the etc directory. So etc directory is going to have all of your login scripts for your profile and for your bash rc resources. So bash logout runs when the user logs out of the system. So often used to clear the screen, clean up garbage, do a bunch of stuff with it. So if you type in more space dot bash profile, let's just see if I have this on here actually. Bash, there's a bash profile. Oh, wait a minute. Bash profile. Well, I'd actually have to see what I have in here. Get myself to the right directory. I don't think I'm gonna be set up the same way, actually. Let's see. My script's going to be different on this computer, actually, because I'm using it. I'm not using standard Linux here. This is BSD. But in any case, the command in the lecture, we'll just use the lecture then because I'm not going to have the same setup. More space dot bash underscore profile. Inside of the, if I had this profile script, in the beginning of it, it would identify itself and it would say get the alias of the function. If I had any aliases or anything set for my environment, it would be inside. And now we're exporting the path and we're unsetting the unset username. So we have a set and an unset. So if this were the logout or the login or one of the scripts associated with my profile, you'll know what they are when you start looking at. You have to see where they're located, probably in the etc folder, and then whether you have a login, a logout, or whether you're using a generic one, or what the name is. It might not just be .profile actually on my system. But long story short, this is just showing you an example of what the profile would look like in terms of you know, some of the things it's doing. An export path is going to take my path and put it out into the environment so I can use it, and then unset my login name and then set my login name upon my login. So my profile will set my login name, because I could be a different user depending upon who's been logged in. So setting defaults for using the VI editor, we don't necessarily need to worry about the VI editor, but if you were using VI, you can actually set a script, modify a script that's used with VI, that loads VI. So use VI editor for code development, configure the .exrc in your home directory, modifies the environment for VI. So you can change the commands around if you want. You can't do it with Nano, but you can do it with VI, which is why a lot of people like VI, because you can customize it, and it's actually more powerful. Nano means small, so it's a stripped down version of VI. It doesn't have the same capability, actually. So it actually automatically sets up the VI environment and set the number of tab spaces as an example to use when nesting lines in code and display line numbers. It does all sorts of nifty stuff. So you can use the test command. So you place the test command inside of the shell script to execute it directly from the command line. And you can actually type in test space in the command. Some users use the test command. Some uses of it might be to perform rational tests with integers, test strings, test to see if something is equal to something in terms of a value, determine if a file or directory exists and what type of file it is, or perform boolean tests. If it comes back true, so you can go test something. Is it equal? Is it less than? Is it greater than? It's sort of like doing a preliminary check on something before you do something. So you can test, is the user logged in? Test, is the user logged out? Test, has the user been logged in for more than an hour or something? And then use that for logic in your script. So here's performing a relational integer test with test command. So equals, greater than, less than, your common Boolean expression. It's not an if, it's a test. So the test command returns an exit status that indicates whether it's a 0 or for true, or 1 for false. Returns a Boolean, essentially. You can write a test inside of your script, actually, instead of using an if-then kind of statement. So I said value is equal to 17. Test the value. Is it equal to 17? It'll come back and say, or echo $, question mark, 0. That would be true. It is equal to 17. So using the switch minus EQ17, test to see if it's equal to 17. So this command, actually, these commands should work in your Unix account as well. So using test to obtain the exit status of 0 in this case. Why do you want to do that? Well, because then you can kind of test to see, is the user's home directory created correctly? Is this the user? Is this the right day of the week? You can test all sorts of different things from the environment, also from variables that are created. So here's performing string tests with test command. So strings are dealt with a bit differently. String obtains the test command here, so we have minus z test to see if there's a 0 length string or whether the string actually exists. Is it, one or more characters. Non-zero string length, meaning that's not a string, it's a 0 or a number, 1, 2, or 3. Non-zero string length. Or 2 strings that are equal, 2 strings are not equal. 0 length, string length. Come back and test to see if it's a string is a string, whether it's set or whether it's blank. So testing files with the test command. So testing numbers or values, environment variables, strings. And now this one is for files. Testing to see if the file exists. Is it larger than, greater than another file? Has it been changed? Is it true if it exists in a directory? If it exists in another directory? Is it a regular file? Is it a directory file? Is it a device driver file? All sorts of different file tests that can be done on that. And then a Boolean test with the test command, come back with a true or false. Boolean operators used with the test command. So the minus A is the logical AND, or the minus O for the logical OR. So test, file exists and file hasn't been modified for a couple days. Or file exists and directory exists. Or file exists and the file has this inside of it. Then we know that some other script that was run that said that the file existed and the secret code is inside of it, or the password code, or I don't know, some unencrypted code or something was in there. So using the test command here, we have an echo minus n. What is your favorite vegetable? Read vegetable. So read is like saying scanf or cn. Read. Put it into vegetables. So if test the name of the vegetable name is equal to broccoli, then echo broccoli is a healthy choice. Else, if whatever you have, then carrots, then carrots are great for you. Else, echo don't forget to eat your broccoli also. And then finish it. End if. So it's just a simple way of running kind of some command line prompt to ask for input and then test using if. So let's see. And test is on if test. So the test part of it's up here. So if test. Because if you went if vegetable is equal to broccoli, depending upon whether the string was read correctly, it could be a capital B, could be a small b. So if you run a test on it, then you know it's equal to broccoli. So it's going to be in there. Formatting a record output. So the record output is formatted using a translate. We've seen this actually. It's in your assignment that you're going to finish up. I'm going to give you some time to finish that up if you haven't done it yet, because we have one more assignment actually to do. So you use the TR to change the characters typed in from the keyboard, and it works as a filter, the input. So it comes from the output and do any other Unix command. So you can run a command and then run the TR and then change the output. Redirect a standard input to come from a file rather than the keyboard perhaps. So here's TR used to change lowercase characters to uppercase characters and replace the colon characters with spaces. So this is slide number 18 of lecture number 6C if you're having problems using a TR command. And what do we have in here? Looks like we've got a grep on a telephone number with a TR that's going to replace the colon with spaces. Take out the colon. It's kind of hard to see this, so I read the slide number for you. And then it will go ahead and redirect the output to the standard I/O. So it's catting the corporate numbers out to the screen. So deleting function, this is actually pieces and parts of a program put together. So if you created a script that put up a menu, and each one of the items in the menu was to add an item, remove an item, delete an item, or change an item. And the items that were being added, removed, and changed were inside of a text file. And the text file was names and addresses. Then this would be the database. This would be the names and addresses in this example. So deleting phone records. The sed command could be used for that. So it takes the contents of the input file and applies a specific action to the file's content. So it sends results to standard output. -D option of sed can be used to delete matching records from the output. So here's the sed, deleting phone records. What we down here is if we run it from our sample menu here, it says corporate phone reporting menu with all the options down here. And this is actually quite typical of what old script menus used to look like, text-based script menus. So the sed command is behind the delete option. So you run the delete and it would run the sed for you. So what you do is you kind of set up, same thing you would do actually in a C program. Kind of set up a text menu that shows up and you put functions in there for each one of the options, and when it picks one of those numbers, you run the function. So the record is no longer in the file. So using the view phone number, you viewed out the file. So if you selected the view option, which was V, then you would see that the telephone number wasn't in there. So hard to see the output on the screen. So if you download the file, download the PowerPoint, you'll probably find it better. Clearing the screen, there's a command to clear the screen, and what you're going to probably do if you're running this little menu is clear the screen after each choice is selected. Refreshes it, makes it look brand new. So clear the screen, run the menu again. So it stores the output of the clear command in a variable and then echo the contents of the variable onto the screen if you wanted to. And about 10 times faster than the actual command, since the system does not have to locate or execute a clear command. It just clears it out. So clear command can be useful for clearing the screen. Other different ways of doing it. I've done it a couple of times. You can look at it, but clear is generally the key word to clear the screen. So you can change clear to clear, and then export clear, and then echo clear. So setting up and using a script variable to clear the screen. You actually have one, or I have one automatically. I don't know if you have one on your system, but usually nowadays most of the Unix scripts will create a clear environment variable that runs a script. And you just run it. It's like echo. It just runs an environment variable. Script, I should say, to clear the screen. So creating an algorithm to place the cursor. One of the things you don't necessarily do with a lot of Windows programs is locate the cursor somewhere else on the screen instead of like where it goes by default at the lower left-hand corner of the screen. So to correct the data entry and the previous data, you can move the cursor block to the erroneous fields, so you can have the cursor go up and down in the menu, or have it underneath the screen itself. So the user hits the minus and then enters, the cursor is repositioned to the start position of the previous field, perhaps, and accomplishes the first step is to create a program algorithm. So you have a sequence of commands or instructions that will result in the cursor being moved. So good practice is to create the algorithms, have developed both the logic shown in a flowchart perhaps, and also conditions necessary to carry out the logic, so you can diagram it out. But here's the example here. So see how the cursor is like way up in the menu there instead of on the bottom? That's done through a cursor repositioning. So creating a program algorithm, incorrect information has been entered by the user. So he puts the cursor where the last name is in this particular case, instead of it. Otherwise the cursor would be right here at the bottom. So you reposition it back up. Let's see, encountered a minus sign and it moves the cursor back up. So if you hit the minus sign, go back up, the plus sign sends you down. So you can navigate through keyboard keys, not necessarily the arrows, but you know, plus and minus as an example to go up and down through the cursor. Depends on how you set it up, actually. You can also protect against, let's say, for example, duplicate data in this sample application. So invalid input necessary because you don't want users to enter. You want them to enter valid data, but what if the person's already in the address book? Then it could check to make sure that there's acceptable information and it's not duplicated. So what most people would do, and this is the same thing with programming in general, we create a flowchart that would start at the top and flow through a series of steps to get to a certain point where you're going to have some sort of a check performed or some sort of an operation performed. So here's the phone ad program. That was this input validation. So what it's going to do on the bottom, you can kind of see this little message. It says the number has already been assigned to, somebody put a telephone number in, but it was already assigned to somebody else. So it'll do a check. So you put a little message out on the screen that says, hey, it's already been assigned. So, functions. So now, at this point, most people go, what's the difference between this and JavaScript? Or this sounds like JavaScript. Or this sounds... Actually, that's the funny thing about JavaScript. And you're like wondering, well, why in the world is she talking about JavaScript? We're talking about Unix shell scripting. Actually, JavaScript is very similar to Unix shell scripting. So those people who learn Unix and learn how to do and comfortable with shell scripting can use PHP, Python, JavaScript, Perl, all those languages, all based on the same concepts. What are the concepts? Setting environment variables, using environment variables, creating functions, creating iterations, using for loops, using files, text files, using data. So the functions are very similar in terms of what you get with C, JavaScript, a lot of the other programming languages out there, scripting languages. They all have this characteristic in common, is that they're very straightforward in terms of being able to use a function or being able to use a if statement or do or while. So a shell function is a grouping of commands all put together. So it's under the same name, like add numbers or log in or log out. Those are functions. So shell scripts can use function names to execute commands, and it executes a series of commands instead of just one command. So it can isolate reusable code and no need to duplicate the same algorithm throughout the program. So we can define a function from the command line, actually. So if you define a function in your shell script, actually I'd save it in a file and then run the file and define a bunch of functions. And then the user just comes up to the computer and types in the function. The function says log out, or function says log in, and that behavior is performed. So, which is actually what happens. Those are functions that run scripts that perform commands for the user. So a lot of commands are functions. So to enter a function from the command line, you enter the name of the function, enter the internal code in the brackets, and the shell will prompt with a forward arrow there for the next line until closing bracket is encountered. And then you have the arguments that are positional. So you have 1 through 9, the $sign. We know about positional arguments and positional variables right now. So creating a function inside of a shell script, creating the function itself inside a shell script supports the reusable code. So a lot of people write the functions inside of shell scripts instead of writing them right at the command prompt, because then they're definitely savable, reusable. Automatically loaded and defined. So if you created a bunch of functions and you stuck the functions inside of the shell scripts to log in, log out, set your profile, the ones that run automatically for you, then you automatically have all this behavior created for you. So you come up to the computer in the morning and you type the name of the function and it does the work for you. What do you mean? Log into the database and do this and do that and do everything else. So you basically don't have to operate the computer. Your shell script can do it for you. A little bit of summary here. Use the first line in the script. Tell the operating system which shell to use with the script. So you can definitely specify which shell to use with each script. Use the test command to validate the existence of a directory or file, or compare numbers or string values. Test it. And sed reads a file as its input and outputs the file's modified content. We saw that in one of our assignments actually. Translate command, the TR command, changes the characters typed at the keyboard, filters input and output and other Unix command information. And to speed up a clearing of the screen, you can assign output for the clear command to a shell variable called clear. Most people already have that created for you though. It's a shell variable called clear, just like echo is a shell variable. And what does echo do? Print some stuff to the screen. And the algorithm itself is a sequence of instructions or commands. And functions help automate those algorithms. In fact, you can load those functions inside of your shell scripts, and you can actually automatically have those functions available. So yesterday somebody asked me about final exam review, and I thought about it last night, and I went, well, the best final exam review I can give you is read through these lectures. So half of you who just showed up missed the beginning part of this lecture. But in this lecture, there's things in here about TR. There's things in here about sed. There's in one of the previous lectures, in fact, this was 6C, by the way, so 1 through 6C. There's information in the lectures about all of the different commands that you're going to be tested on in the final exam. The final exam will be multiple choice. It's based 100% off of the lectures and the assignments. More on the assignments, actually, because that's how you're using the commands. So it'll be a combination of multiple choice plus fill in the blank, or short answer, where you're not writing words, but you're writing commands. So the best way to practice and the best way to study for this exam, I don't even have to have a final exam review because I just told you. So here's our final exam review. I'm telling you the commands, the information in the lecture, which is why I'm presenting this stuff to you. All of the lecture material that I've covered to you. And if you're wondering, what have I given you so far? Let's take a look. To date, I have a little bit more to give you, but we're not done with the course. But what you want to do is, if you go into the Unix folder, we did 1, 2A, 2B, 3, 4, 5, 6A, 6B. We're up to 7. 7's the next set of lectures I'm going to give you. 7, 8, 9, 10. That's what we have left for this course. This is the testable material along with all 7 assignments. That's your final exam review. So that's what you want to do. You will have a final at 3 o'clock, and the final will be about 2 hours in length. You'll have to write some commands and have to answer some multiple choice questions. Do we have any questions? No. Okay, let me stop this recording. Oh, do we have a question?
3 o'clock on 16th?
I believe that's the last weekend, the 15th, 16th weekend. It's not next weekend, it's the following weekend, which is why I'm kind of telling you now, because like you were concerned yesterday with getting the, I just gave you the review. I'm not going to go through and tell you about the TR command all over again, or the sed command, or the grep command all over again, but you want to know what sed, grep. So what you could do if you're bored, you could go through the lectures and make a little to-do list, or I think you're probably doing it already, with all of the commands I'm talking about that are repeated in multiple lectures. So grep's on there, TR's on there, sed's on there, cat's on there, echo's on there, and just be familiar with those commands, as well as the underlying concepts. I gave you some kernel information yesterday. process information, thread information. Yesterday was all about kernels and Unix operating system, essentially. Today is going to be more on scripting, and I'm going to give you some lecture on networking stuff, pinging and networks and stuff like that, network commands. That will be coming up soon. And Saturday I'll give you some more information. We'll finish up whatever we don't finish up today. Sunday morning you'll have a little bit of time to study. So you'll have some study time because it's kind of odd to give you an exam the same day of presenting new information. So there'll be an opportunity to finish up your CSLO essay and also to work on a few things. So, all right, so let me stop this recording.